Welcome to Biogas Basics. My name is Jürgen Kube. This is part 2 in the mini-series about the mass balance of a biogas plant. The first part described the fresh matter and dry matter mass balance of a plant with known and constant biogas yields. In the second part of this mini-series, I will extend the mass balance to organic dry matter and nitrogen. We reuse example 1 of the previous presentation. A biogas plant with a primary digester that can operate at 12% total solids and a secondary digester that can operate at 9% total solids. The digestate is fully separated, and only solid and fiber-free liquid digestate leave the plant. And like in the first presentation, we split the AD plant in 2 subunits, the biogas production and the separation step. We ignore all internal recirculation and dilution streams. Now we need to define how each species behaves in the substeps. How does the fresh matter, dry matter, organic dry matter, total nitrogen and total ammonia nitrogen split in each process step? For example, how does the nitrogen behave in the digestion step? First, we separate the total nitrogen into organic nitrogen and total ammonia nitrogen. As a reminder, total ammonia nitrogen is the sum of ammonia and ammonium nitrogen. Total nitrogen is the sum of organic nitrogen and total ammonia nitrogen. During the digestion step, organic nitrogen in the feedstock is converted into total ammonia nitrogen. We quantify this with the nitrogen mineralization degree. The amount of total ammonia nitrogen produced in the digestion step is the mineralization degree times the organic nitrogen freight. We can calculate the nitrogen mineralization degree from the biogas yield and the biomass yield coefficient. See my feedstock presentation for more details. We know the total nitrogen in the feedstock, the amount of biogas produced, the mineralization degree, so we can calculate the total ammonia and organic nitrogen concentration in the average digestate. Here are the calculations in Excel. First, we copy the feedstock properties, now extended by loss on ignition, organic nitrogen and total ammonia nitrogen. We calculate the respective mass flows from the properties. Then we calculate the biogas mass and the TS of biogas. We set the LOI of biogas to 100%. Remember the definitions in the feedstock presentation. Substrate plus water reacts to biogas and biomass. Organic dry matter is substrate plus inert organic dry matter. So all the dry matter of the biogas is of organic nature. To balance nitrogen in the digestion step, we need to calculate the nitrogen mineralization degree. The idea is that nitrogen is converted in the same ratio as organic dry matter in the feedstock. Some of the nitrogen is used in the biomass buildup, and the excess nitrogen is converted to total ammonia nitrogen. The amount of total ammonia nitrogen released in the digester is the organic nitrogen flow in the feedstock times the nitrogen mineralization degree. We add this term to the biogas mass flow. Biogas is an outgoing flow, so the term is positive. The same term with a negative sign is put into the total ammonia flow. The biogas flow does not contain any organic nitrogen or negative total ammonia, but we use the biogas flow as a reaction flow. Then we balance fresh matter, dry matter, organic nitrogen and total ammonia nitrogen by subtracting biogas from feedstock to get the average digestate. In the last step, we calculate the average digestate properties. It contains 0.48% total ammonia nitrogen, which is 4.8 kilograms per ton. However, this does not tell us the total ammonia nitrogen content in the effluent of the primary digester, which is the important number when it comes to nitrogen inhibition. In the next step, the average digestate, index 1, is separated into solid, index 2, and liquid, index 3, digestate. Now we define a solubility sigma for each species. The species concentration in the solid digestate X2 is a linear interpolation between the 2 extremes. The concentration of X2 if the species X would be completely insoluble, or sigma equals 0, and the concentration of X if sigma would be completely soluble, or X equals 1. The formula is X2 is sigma times X2 if X is completely soluble, plus 1 minus sigma times X2 if X is completely insoluble. The table shows 3 extreme scenarios. An insoluble species in the first row, a species soluble in fresh matter in the second row, and a species soluble in water in the third row. For the insoluble case, sigma is 0. The mass flow of species X is indicated with a capital X. In the insoluble case, the ratio of the mass flow of X in the solid digestate to the mass flow of X in the average digestate is the ratio of the dry matter streams in the solid digestate to the dry matter stream in the average digestate. When X is insoluble, it behaves like dry matter in the separation step. The concentration of X in stream 2, denoted by a small x, is X2 equals X1 times TS2 over TS1. The insoluble case is the same for both cases: species soluble in fresh matter or species soluble in water. If the species is soluble in fresh matter and sigma equals 1, the balance is that the ratio of mass flows of species X in the solid digestate to average digestate is the ratio of the respective fresh matter streams. For example, if 30% of the fresh matter stream goes into the solid digestate stream and the species is completely fresh matter soluble, 30% of the species mass flow ends up in the solid digestate. The concentration of species X in stream 2 is the same as in stream 1. The separation step is not selective against species X. Examples for this behavior are substrate fractions, ash and organic nitrogen. We will use the concept of substrate fraction later, when we start using kinetics. If the species is soluble in water, the mass flow of X will behave like the mass flows of water in the separation step. The mass flow of water is the difference between the mass flow of fresh matter and dry matter. The concentration of species X in the solid digestate, X2, is X1 times 1 minus Ts2 over 1 minus Ts1. The classical example for this behavior is total ammonia nitrogen or volatile fatty acids. Basically all species that are water-soluble and are present in small concentrations. For the organic dry matter balance, the formula is slightly modified as we balance the ash content, which is Ts, times 1 minus loss on ignition. The formula for the loss on ignition of the solid digestate is solubility of ash times 1 minus LOI, 1 times 1 minus Ts1 over Ts2 plus LOI1. The organic nitrogen is fresh matter soluble, but the concentration is dry matter related. The concentration of organic nitrogen in the solid digestate is Tn, 1 times sigma Tn times Ts1 over Ts2 plus 1 minus sigma Tn. For total ammonia nitrogen, the concentration in the solid digestate is the concentration in the average digestate times the solubility of NH4n times 1 minus Ts over 1 minus Ts1 plus 1 minus the solubility of NH4n times Ts2 over Ts1. This solubility method seems a bit over-sophisticated at first, but it has one advantage. No matter how we select the solubility parameter, as long as it stays between 0 and 1, the mass balance can never create negative mass flows or unreasonably high concentrations. Here's how the mass balance of nitrogen and organic dry matter for the separation looks in Excel. We calculate the amount of solid digestate with the rule of levers from the Ts of average, solid and liquid digestate. Now we define solubilities for ash, organic and total ammonia nitrogen. We choose a 30% solubility for ash, meaning that 30% of the inorganic dry matter are fresh matter soluble, for example in the form of soluble salts. 70% are insoluble, like precipitated salts or agglomerates. Organic nitrogen is mostly bound in proteins, and is probably not very soluble. Total ammonia nitrogen is 100% water soluble. This is the worst case for nitrogen accumulation. It is likely that some ammonium ions will stick to negative surface charges of particles in the digestate. We calculate the loss on ignition of the solid digestate with the solubility formula. Note that the formula works both for the solid and liquid digestate. We then calculate the organic dry matter flow of the solid digestate. Same for organic nitrogen. Finally, we calculate the total ammonia nitrogen concentration of the solid digestate and its mass flow using the formula for water solubility. In the last step, we balance the liquid digestate as average minus solid digestate and then calculate its properties. We see a slight concentration of total ammonia nitrogen in the liquid digestate. It increases from 4.8 kg per ton in the average to 5.2 kg per ton in the liquid digestate. The organic nitrogen seems to accumulate as well, from 3.6 to 4.3%, but its concentration is dry matter based and the total solids changes from 13.4% to 5%, so organic nitrogen is concentrated in the solid digestate. At this point I have to address a biogas myth, that the recirculation of process water will lead to an accumulation of total ammonia nitrogen in the digesters. This is not the case, or only to a very small extent. The idea is that process water generated by separation contains total ammonia nitrogen, at the same concentration as in the digestate or even slightly higher, and that by recycling the process water back into the digester, the NH4n levels increase slowly over time. However, for this to be possible, two things need to happen. First, the biogas plant must make very little liquid digestate, and second, the separation step must selectively move total ammonia nitrogen into the liquid phase. Both cases are unlikely. In the steady state, the total ammonia nitrogen stream leaving the plant in the solid and liquid digestate is the total nitrogen mass flow in the inlet times the mineralization degree. In the worst-case scenario, with infinite dilution, the concentration in the digester effluent can only reach the concentration in the liquid digestate. In reality, the dilution is not infinite, and the concentration is somewhere between the concentration in the average digestate and the concentration in the process water, depending on the dilution ratio. Let's break it down. We balance the digestion step by subtracting the biogas from the feedstock and convert organic nitrogen partially to ammonia nitrogen. The result is the average digestate indexed with D. In a second step, the average digestate is diluted with process water that also contains NH4N to create an effluent indexed with E. If the separation is not selective against total ammonia, its concentration in the process water will be the same as in the average digestate, and the concentration in the blend of the two fractions will be the same, regardless of the mixing ratio. Only if the concentration in the process water is higher than in the average digestate, the concentration in the digester effluent can rise. We can quantify the rise. The mass flow of average digestate is m dot. The process water stream is R times m dot. The TS of the effluent TSE is TSD plus R, times the TS of the process water TSPW over 1 plus R. The same mixing rule applies for the total ammonia concentration in the effluent, the concentration that influences the toxicity of ammonia to the microorganisms in the reactor. It is 1 times the NH4N in the average digestate plus R times the NH4N in the process water over 1 plus R. Ammonia is water-soluble. We can calculate the concentration in the process water from the concentration in the effluent using the solubility rules from previous slides. The ammonia concentration in the process water is the ammonia concentration in the average digestate times 1 minus the TS of process water over 1 minus the TS of the average digestate. We simply balance over the whole AD plant in steady state, which is independent of internal recirculation streams. Now we can calculate the total ammonia concentration in the effluent. Let's visualize this with the help of an example. The TS of the average digestate is 17%. The digesters require dilution to 7%, with the help of process water with a total solids of 5%. We can calculate R with the rule of levers. It is 17% minus 7% over 7% minus 5% of 5. 1 ton of average digestate of 17% must be diluted with 5 tons of process water to create 6 tons of digester effluent with 7%. I deliberately chose the values so that the recirculation is very high. Typically, the recirculation ratio is less than 1, or the digesters would become too big and inefficient. The ratio of total ammonia nitrogen in the process water to average digestate is 1 minus 5% over 1 minus 17% or 114%. We can calculate the total ammonia nitrogen in the effluent with the mixing rule shown above. It is 112% of the concentration in the average digestate. So even in the extreme dilution scenario, with a 5-fold recirculation, the total ammonia nitrogen in the digester effluent is only 12% higher than the concentration in the average digestate. The real reason for high NH4N concentrations in digesters is the high total ammonia concentration in the average digestate, not the recirculation of process water. The total ammonia concentration in the average digestate can be lowered by adding external water to the diet, which will lower the TS of the average digestate and the requirement for process water recirculation. From the operator's perspective, it will look like the reduction of recirculation after the addition of fresh water will lower the NH4N concentration in the digester effluent. But it is the fresh water that does the trick. Alternatively, the recirculated process water can be stripped to remove ammonia. This will not lower the total ammonia concentration in the average digestate, but it will lower the concentration in the digester effluent. To recap, process water recirculation will not lead to ammonia accumulation in the digester. A high total ammonia concentration in the average digestate is the culprit. To summarize, we extended the fresh matter dry matter mass balance with organic dry matter, organic nitrogen, and total ammonia nitrogen. The biogas yield is still constant and known. To balance the additional species, we need to understand how they behave in a digestate separation step. The solubility parameter defines how the species behaves in the separation step. It describes how the species falls between the extremes, total insolubility and total solubility. For the total solubility case, we will need to distinguish if the species is fresh matter or water soluble. Species that are present in high concentrations are typically fresh matter soluble, whereas liquid species that are present in low concentrations, such as total ammonia or volatile fatty acids, are water soluble. I showed the mass balance in Excel, so this can be easily replicated. Stop the presentation if necessary to examine the formulae. And finally, we addressed the biogas myth of total ammonia accumulation when process water is recirculated. the recirculation does not cause total ammonia accumulation. Instead, high total ammonia concentrations in the digester effluent are caused by high total ammonia concentrations in the average digestate. This concludes part 2 of this mini-series about the mass balance of a biogas plant. So far, we have assumed that the biogas yields are known constant values. In reality, the biogas yields will depend on the residence times and number of stages in the digester system. In the next part of this mini-series about the mass balance, I will introduce the concept of biogas potentials, biogas yields, and conversion factors. We will then use kinetics to predict the impact of residence times on conversion factors. I'll see you in the next episode of Biogas Basics.